Yes, but when it comes to, yes, you are muted.
Okay, then we come to the second part of today. And the first part, which sort of really talks about things which have not materialized yet, but which might happen in the future. And sort of boldly enough, I'm claiming that this is the future of HPC programming. And we're starting with type-safe generics. So for today, tomorrow morning, and tomorrow afternoon, we're going to go through these three parts. Type-safe generics has a very strong focus on API, and it will touch into integrated domain-specific languages. I will explain that when we get there. Also notice that Fortran generics is sort of planned to be in the 2020Y release. The 2020X release is coming out next year, so hopefully it's 2023. It's sort of making its way through the necessary ISO processes. But in the meantime, there's lfortran.org, and they're very lean forward. But this is an extremely prototype compiler, so it doesn't do everything it should do, and it doesn't do everything it should do really well. But at least it's possible to do some prototyping of generics there. And interestingly, they have run in the browser version. So you can go to this web address, and there are some generic examples that actually work in the browser. Also note that all notation per now is completely indicative because no syntax has been okayed by the Fortran committee so far. Was it anything?
Someone wants to move the camera.
Okay. Tomorrow morning, I will go into definitions of code and discuss mathematics of arrays and what it sort of can do for you. And then at the end of the day, we will look into interpreters for Fortran code and see how that sort of can open up new possibilities for software development and playing with software. And all of this sort of hinges on type-safe generics. So it's a really game changer if everything works out. So plans for this afternoon more specifically. So I will explain my perspective on software development a little bit. I will take you into the world of Fortran generics, use some time for that. And I will relate this to C++ generics for those who have heard about generics from the C++ side. And I will gently take you from here into this domain-specific language setup. And hopefully you will demand from your compilers that they give you templates now and don't wait another 6 years before they start working on it. Which, by the way, is the general message from compiler vendors doing Fortran. You won't touch it until it's in the standard. A little bit about me. It sort of seems to be compulsory explaining where you're from. So I started programming Fortran 77. And then the university changed their courses to use Pascal, at least introductory courses. And when I started teaching, I came up with something called generic Pascal. Well, they didn't call it generic Pascal, but it basically was Pascal with generics. So basically, I've had generics experience quite a long time. Note this is before C++. Then we had a project where we developed coordinate-free numerics. That was very interesting because we really needed generics to run the software, build the software the way we wanted to build it. And the only commercial compiler around was C++. And we had lots of quarrels with different vendors about their template implementation not being correct. And we also made a special issue of Scientific Programming Journal about sort of coordinate-free numerics and what this was about. The better introduction paper is actually published in the Nordic Journal of Computing, which sort of seems to have passed away, even though it hasn't been publishing issues, number of journals for a long time. We started the Bergen Language Design Laboratory more than a decade ago, where we're looking into programming language concepts, programming language tooling, domain-specific DSLs, and the relationship to APIs. We also started our own programming language, which my students said should be called Magnolia. They had a good reason for this, about a sturdy magnolia flower being very strong and sturdy and resistant to bugs. The good flavor here is that we based the language design on a theoretical framework, institution theory. So it's sort of not the things we like and dislike, it sort of really has a complete setting, which integrates specifications and programming with the aim of doing like HPC as one of our domains. Another interesting thing here is that it has very powerful reuse mechanisms, and it is sort of basically a testbed for generic programming, type-safe generic programming. So when it comes to 2019, let's say, before that I was involved in some small project on modern high-performance design patterns for Modern Fortran, which is much about using object orientation to encapsulate abstractions and make your Fortran sort of fit your domain in a better way, which was also programmed in Progress in Scientific Programming in 2015. And I was coerced, basically by one of the co-authors, to present a perspective on generics at the ISO meeting in Tokyo in 2019. And the perspective and presentation we gave there sort of seems to form the way that Fortran will approach generics. And the basic thing there is get type safety in there and be simple. If it's difficult to see where we should be going, probably don't add it now, add it later when you get more experience. So the first template version in Fortran is going to be very slim and focuses on the essential things, and we try to avoid the difficult parts of Fortran because we don't know how they will interact with the template mechanism. And right now I'm sort of an alternate in the Insights Committee, which is sort of in the ISO system, the committee that is responsible for the evolution of Fortran. And I'm sort of what they call an alternate for the National Center for Atmospheric Research, and CAR, which is those who do climate models and research on weather models and gather lots of... Yes, very nice building up on the hillside. Exceptionally nice. And I'm a member of the subgroup on generics. So interesting, WG5, which is the nickname for the insiders, is old sort of subgroup of ISO responsible for Fortran. And J3 was sort of the ANSI name for this group doing Fortran back in at least 1990s. And those names are sort of still sticking inside the committee, even though officially these names are completely non-existent. A little bit about my perspective on programming. And we need to think about programming languages as defining formal systems. And as a formal system, they have their own mathematics, their own way of reasoning about what software is, what your program does, what the modules you're using. It's sort of formal mathematical objects worth a study in themselves. It's not just something that's there for your needs, it's also something that's worth studying. And the moment you look into this fairly deeply, trying to study what this is, it really gives you a different perspective on how to develop software and think about what software should be. Now, if you heard about Haskell, those people working with that are sort of really pushing software as a mathematical object, and they shroud lots of their papers in advanced categorical terms, trying to explain what is going on. And personally, I find lots of this difficult because they're using high-order functions as something sort of primitive in their language, but higher order sort of makes for very difficult semantical models. Magne is another formal system which we've actually been studying from various perspectives, and it has much simpler semantics based on set theory, and in that way it's sort of closer to Fortran, C++, C languages, which are sort of more typical HPC languages and have this sort of very more sort of simplistic semantical model. So my perspective on Fortran semantics and these other languages is that the data that you declare, your data structures, basically boil down to bit patterns on the computer. So what you're working with is sets of bit patterns. Now, sometimes you think about them not as sets of bit patterns, but as approximations to sets of integers, sets of reals, etc. And I want my semantical model to allow you to think about these as mathematical objects or think about them as bit patterns, and both of them should be consistent with what you're doing with the software. And if you look at procedures, well, at one level there are formal mathematical functions mapping bit patterns to bit patterns, or they are computer instructions manipulating bit patterns to bit patterns. And we know that there are different instructions interpreting the bit patterns as floating point, or as integers, or as some other data type we're working with. Or you can consider procedures as algorithms, and there are executable models which sort of runs on the computer. So it's sort of, in some sense, down to earth, hopefully very close to how you program, how you think about computers. So in Fortran, you have some types of data. They are the intrinsics, which are sort of these types, logical and others. And then there are the user-defined derived types. And these correspond to struct in C++. And actually struct and the class in C++ are synonyms with sort of opposite defaults for some of their settings. And you can have arrays of the above, but you cannot have arrays of arrays in Fortran, which is an anomaly when compared to other programming languages. There are historical reasons for this, and it's been preserved because this allows Fortran compilers to efficiently map the array computation on the computer. But it also forces you to write your software in strange ways until you have got the right types. And we'll sort of discuss this a little bit tomorrow. Procedures, yeah, those that come with the language, those that you define yourself. And interestingly, you can say that the procedure is elemental. So it doesn't just work on, for instance, integers or reals, if that was your data type, but you can apply it to arrays of integers or arrays of reals without having to do anything. You don't need to write a loop, you just apply it to the corresponding list of arrays, which then have to match up so that the shape of all the argument arrays and the result array matches so that you can apply the function. So this is like the map function, which functional people are so proud of, but Fortran has this built into the language. You don't need to call a higher order function to do the map, you just have it. And on top of that, this is naturally multi-argument, while in functional languages you have to work hard to deal with multi-argument functions mapped across lists. So it's interesting from this perspective, Fortran is very well advanced. So Modern Fortran, which we heard quite a bit about this morning, it started out procedural, and you can write procedural code. You also got object orientation, with divide data types and type down procedures. It has arrays, which I mentioned, and coarrays, which is sort of the parallelly distributed array data structures. And you can also write functional expression-oriented code. Now, in the functional setting, functional means higher order and stuff. But in the Fortran setting, functional means that you're writing clean expressions with no side effects. If you look at C++, it's interesting because C++ is procedural in the same as Fortran is. You can write in a procedural subset. Much of that comes from C. We have object orientation, which was sort of one of the selling points back in the 90s for C++. And since they introduced templates, generic programming is sort of becoming more and more important. And after the standard template library, it really changed the way you could think about programming C++. It was using templates in a way that Bjørn Straustrup never had thought about, but in a way he thinks is the right way forward. And this was sort of part of what was called Modern Fortran, an effort between Herb Sutter and Bjørn Straustrup in sort of focusing on the better parts of Fortran. So what is happening now is that they're trying to move away from object orientation towards generics, meaning that the encapsulation of object orientation is paramount for this to work. And also, if you look at much of the code, they can use static inheritance, but don't try to avoid virtual functions because they tend to slow things down. So general programming models, procedural sort of was the structured programming back in the 1970s. And Fortran took some time to really catch up on that. Functional is sort of no side effect programming, expression oriented. Haskell has higher order fancy type system. Expression oriented is what I find important here. Object orientation, sort of what we talked about, and generic programming. And if you want to read back on that, there's a book by Alexander Stepanov and Felix Jones. Stepanov was the guy who worked at SGI and invented the STL. So he's been very influential in how Bjørn Straustrup and the C++ community thinks about template programming. And this book is now available for free if you go to this webpage. And as I mentioned, modern C++ is shifting away from OO towards generic, even though you need to use the abstraction mechanisms of OO to go there. So what is in a template? Think C++, think the future of Fortran. So you need to identify what the template is about. You need to list up what are the template parameters. And you need to sort of talk about not just how they are, what they are named, but also what they are supposed to mean. And then there's the template body where you write your templated code and you get sort of to the meat of what is going on. So here's a short comparison between what we hope will get into Fortran, the current thinking on the Fortran design, versus the choices that C++ made. So in Fortran, a template is always a block. In C++, a template is a template class or a template function. So a template class is sort of has a block inside, while a template function is sort of maybe even the individual functions inside the class. So this one seems to be slightly simpler than the block approach for Fortran. But and also Photon then needs the nested templates to be able to get to the flexibility that C++ has here. In both of them, you list what the parameters are. In Fortran, you have to declare them. That's called requirements. They're compulsory. You declare every parameter. Is this a type? Is this a function? What is the function? What are the arguments? What are the self-type? And so forth. In C++, declaration of the parameters is somewhat optional. You can do that directly in a parameter list, or you can do that as concepts. Concepts is an addition to the template mechanism in C++. And what they have now is called weak concepts, because it can only check instantiations, it does not check the template body. This is very important to notice. So inside the Fortran template body, it will be type checked. So once you write the template code, you will also know from the compiler whether this is consistent, type correct, also meaning that every instantiation will be correct with respect to the requirements. In C++, the template body is not type checked. The instantiations are type checked. And also, if you write a concept, sort of clearing your arguments, there's no mechanism in the language which will check that the concepts you have said or the declarations you have given are consistent with the body. So this opens up a certain dynamic approach, but it also takes away lots of possibilities for advanced generic programming. Yes, C++ is horribly advanced. You can do C++ metaprogramming. In the Fortran version, we are not tying metaprogramming with the template mechanism. Doing that was an accident in C++, and we don't think that's a good idea for Fortran. If you want to do metaprogramming, introduce metaprogramming constructs in the language, which is what C++ is doing with static reflection, for instance. So let's move towards an example. This is sort of a short travel app. I've been flying from Bergen to Stockholm and from Stockholm to Umeå. The question is, what was the speed I was traveling these two legs of my travel? So to talk about that, I introduce type D for distance. I introduce a type T for time duration, and I introduce a type S for the speed. And we can see I've listed those as template arguments, parameters. Also, I have listed out 3 functions. The first function, plus B, is addition on distance. So it sort of says there's a function called plus B, it takes 2 distance arguments and returns a distance value. So I'm adding distances. I can also add time durations. So I take in L and R, that give type time, and I return something of type time. And then I have a divide operation. I can divide distance by time, and that will give me the speed I'm having. Notice that I haven't introduced addition of speed, and there are other functions that might be useful, like being able to divide distance by speed and get time and things like that, which isn't in this declaration set. So I'm just declaring what I need to be able to compute the average flight speed on these 2 legs of my journey. And I've prevented myself from accidentally adding 2 speeds and trying to divide by 2, because the addition of speeds is not in my vocabulary. And here's my template code. So I said travel template, list the arguments, and I say requires that these arguments have to follow the declarations I had on the previous page, and that was the requirements, which was named travelers. So by doing this sort of required statement, I'm declaring all these parameters to behave as I said on the previous page. And now I'm implementing my function, average speed from time, and I have d1, t1, distance 1, time 1, distance 2, time 2. And then I can do the addition of distances, I can do the addition of time, and I can divide distance by time. And the vocabulary I've given myself here, the correct operations I have, sort of prevent me from doing much more. So if I was sort of in high school, this would prevent me from making the mistake of adding 2 speeds and then dividing by 2 to get the average. because this is now weighted with the distance I'm trying or flying. So you see that we can use this mechanism to limit the mistakes we can make or are making in writing code. And the compiler would flag or should flag any deviations from this in the same way. So it would flag any deviations if these had been sort of different derived data types in Fortran. We wouldn't be able to do anything besides those operations that were included with the data type. Generics gives me the same, but with a derived data type, I have the encapsulation, I have the overhead of building that data type. And then for these computations, I would have to sort of decompose that, look at the fields and do the actual computations for these addition and divisions operations. But with the template mechanism, I'm not stuck with that because I can say that distance, time, and speed all are reals. So there's no overhead for these operations. At the moment, I'm saying encapsulating this, having a wrapper function, add real, and slash real. But our intention is for you to be able to write, should I fix that in my slide? Write operator plus, which is the Photon notation, and operator slash directly in the call sets here. So I would be using the intrinsic plus, and the intrinsic division operation on reals. So the instantiation would have been, gives me the same efficiency as if I was computing directly with the reals, but I get the type safety of explaining what my parameters are supposed to do in my template body. So I'm getting the speed and efficiency of normal Fortran code, but the reusability, some extra type safety, and a larger reusability. And here's a small program which does the computation, prints the output, and runs the test program. So this is roughly the notation that we will have. I should really have misplaced these with the proper notation, but this actually works in the prototype Fortran compiler. So you could sort of go there and do this online now. Do you want to see that? So here's the setup. Some people in the chat. Anything interesting in the chat?
Not in this chat, not in the other chat.
Okay.
You might want to take on a laptop, the left-hand side is quite small.
Let me see if I can increase it. Yeah. Make it slightly larger, but then we're sort of starting to lose things on the right-hand side. For now, I had to create wrappers. So here's a wrapper for integers, add, mult, minus, etc. And here's a wrapper for reals. And there are modules which I just can import later on. And here's the module travel, where I have the requirements section. And this sort of gives me the declarations of plus times. And this one does a slightly larger example. So this is the d divided by t that I showed on the slide. And here's the d divided by speed, which then returns sort of the time. If I have a distance and I have a speed, I can compute the time. And here's the template. And it takes DTS, the three types. It takes plus of d, plus of t, d divided by t, and d divided by s as its parameters. And then it says requires travel ops, which means that each of these will be matched with the corresponding declaration up here based on position. And then the compiler knows these declarations are associated with these names. So for readability, the names are the same, but that's not necessary. Probably. So here's average speed from time. And this is the computation we saw, plus d, d1, d2, plus t, t1, t2, and divided by t. And here's this other function. We should export that, but make that public as well. And then we have a different computation here. Now, if I say divided by s, this was the one I put in from the outside. So if I delete this one and try to replace that with a division symbol, and now I try to run it, it means run and compile. And you can see that it detects that this slash operation isn't for dividing d by speed. So the type checking tells me that at this stage already I'm probably doing something wrong. Even though division is my intended operation, it doesn't match the typing that I have, so the compiler will detect that this is a problem. And this is the point of type-safe generics. Yeah?
So what, I'm trying to get my head around. So type mismatch. So essentially, because you declared it's a function which connects D's and S's.
Yes.
This is division is a function which connects fields, and therefore you get a type mismatch.
Yes.
Is that the
Yes, yes. Now we would be able to overload slash on different types in sort of in the future generics, but right now I cannot do that overloading, so this will definitely be a type error. So yes, it's because slash is from real to real. We haven't made an overload for distance and speed, so therefore this is a type error. So I'm getting this type safety out of the compiler. It prevents me from making mistakes. Right now it prevents me from making a nice notation, but it will prevent me from adding time and distance, for instance. I can only add distance and distance, and time and time. I cannot add time and distance. I cannot add speed and speed. This is sort of the limitations I've given myself. We could do all this with object orientation in Fortran if we introduced our own derived types for speed, time, and distance. Don't you agree, Jonas?
Yeah. I just get the point around where, so you declare D, S, and T.
Yeah.
And then you give them as real.
So in the object oriented, the S and T would have one data field, and that would be the real value. So that means I would, when I wanted to do additional to distances, I would have to peek inside my type to see the two fields and then add them together to create a new distance object. But here I'm saying I'm assuming I have a distance type, I'm assuming I have additional distance. So therefore I can use those two operations when I'm writing the code. So I'm assuming the things that you otherwise could code into a language. So this gives us an advantage when it comes to using it, because now I don't need to say, here's an implementation of distance, here's an implementation of time, here's an implementation of speed. I can say which data type I will use in that setting. And the data type I want to use in that setting is for type real. Because type real has all the functions I need to match up with my intentions. This is why I'm saying this is a game changer, because I don't need to create all those wrapper types to have the same type safety, and I get the full efficiency out of it. Yes?
If I take your example and I want to make it double precision, what would I need to change?
Nothing in the example itself, let me just correct it. So undo my typing. The meat of what you're doing is down here, where I'm instantiating the travel template with these wrapper types for the moment, but directly with the operator plus, operator slash, according to our intended syntax.
So I would need all the stuff in the bracket I would need to change.
So how do you write double in Fortransk?
Double preposition. Old-fashioned F77.
I forgot it.
Double preposition.
That's the name of the data type.
This is an intrinsic name from the old days, but you can put in some name there, like Real 64 or something.
So this
Two words.
double precise, something like that.
Yeah, exactly.
Yeah, and then I would do that here and here. And if I could write operator plus, then that would be all I needed to do. Now, in this case with the wrappers, I probably need to have wrapped the double precision version as well. But this is the intention of just being able to write operator.
But I'm getting it right. One of the things is I write it once, and if I have complex or whatever, I just change that line, and then everything is done.
Yes. So that would be the instantiation in this setting. And I can move to complex, I can move to integer, and I can change the position of my real numbers without any problem.
There's a question in the answer document. It says, amazing and very nice. Are there any plans to make the notation less verbose before becoming standardized? Currently, it feels to be a lot of typing.
That's the Photon style. Photon has lots of typing for its declarations. We're trying to simplify it, but we're scared of simplifying too much now and ending up in a corner later on. So we stick with the Photon declaration style. Yes, it's a bit verbose, but if you notice, I am if I go up to the template, here I am saying requires travel. So I'm importing and reusing that declaration. I can use this same set of declarations like this in other templates. And that's an important feature because we foresee that we will have fairly large declarations of requirements and they can be reused in many settings. So yes, you have to type quite a lot the first time, but then you can reuse it where you want to use it. And I know C++, when they were doing things like the concepts, they were putting lots of emphasis on making very compact notation for the simple cases, but they could not make compact notation for the complex cases. We're sort of saying, well, we don't know enough about future use to dare making compact notation for the simple cases now. Let us get some experience and then we can see what turns out to be the simple cases. The reason we are a bit scared of that is that once we start using this template mechanism, we see that we can exploit it in settings we haven't foreseen yet. And if you have made commitments to being too simple in some cases now, maybe those were not the best cases to give that kind of syntactic support. So by being more regular now, we're hoping that we can easily simplify things later on when we know what should be simplified.
If I understand right, the travel implementation DTS, you have to implement a plus D and a plus T for the types that you want to support.
We have, yes, we're saying that there's two things going on here. One is that we have declared what, like B divided by S, which is over here somewhere, is supposed to be what our intention is with that type. The body of the template is using that intention, otherwise you have a syntax error. So we are sort of certain that in the body here, we will not be making the mistakes that prevented us from making by these declarations. When we come to the instantiation, we have to choose what we want to do. And then at the instantiation time, we are sort of saying, is this double precision? Is this simple precision? What are we aiming at to achieve with what we are doing? And then you want to be able to write, as I was showing, just operator plus here. And then Fortran has to figure out which of the variants of operator plus I'm talking about. This requires the compiler to peek inside the declarations of the template to match it up with the type argument and then see if it's possible to figure this out. So it is sort of asking the compiler to do new tricks. And there's a discussion going on between us from a user perspective wanting the simplicity and some compiler vendor wanting to have more explicit declarations so it's easier for them. But the two compiler vendors in the generic subgroup, they're quite convinced that this doesn't put too much burden on them. They think they can relatively easily support that. Yes?
There's another question. Did you already say which Fortran compiler is giving all this facility? Generic programming question mark.
None, because the syntax hasn't been defined yet. But Fortran seems to be prototyping this. And I'm in dialogue with those people about making these examples work. So if you go to the Fortran webpage, lfortran.org, you should be able to sort of find your way around it. And that's open source, and the examples, some of the examples are open source. Those examples that work with a compiler right now are available. I'm not certain there are links.
So there is, LLVM,
Yes, Fortran uses LLVM as the backend, but all of the template processing is in the, not the front end, but the intermediate end and the front end. And the reason we can run it in the browser is that it produces also WebAssembly output, and they compile the compiler to WebAssembly so we can run it in the browser, which is nice. But there's some quirks in the current notation here, so it's not easy to sort of match what they can do right now. But this is an example which does it. So we now fixed that error. We probably introduced lots of new errors with the modifications we did. Let's see. Yeah, token precision is unexpected. So we'll undo all these fantastic changes.
So I'm pretty sure some fixes, unless we make spelling mistakes, they need to be able to digest them.
Let's see, it should run now, I think. Yeah. Now that it actually is running, you can change one of these numbers. And
real A. We have a long-standing discussion. Real bracket open, A bracket closed. It works with most compilers. So assuming that double precision is kind 8, but it is not in the standard.
No.
And I have seen a lot of Fortran examples which do not obey that.
yes,
So I always go, if I see it from a student hand in, I go ballistic and fails it. Fails their hand in.
I had it on a slide at some point and you saw it.
You can either define the types yourself by using the kind things and so on and ask for so, or use the ISO standard where it says real 64 and real.
Exactly, but so the GCC and Intel real
It's
brackets 8 word
Yeah.
kind of double precision is.
But does it work on the Cray compiler?
There was an ancient Fortran in GCC, and they had 1, 2, 3.
Yeah, so yeah, that's my point. I mean, you never know what you're gonna get, so.
the editor of the standard says that the arguments to real, the kind is a magic number. And if you want to have control over it, there are certain intrinsic functions that will identify the position you're looking for.
Kind of 1.ODO.
1 point.
ODO. 1.0DO is a one in double precision.
Oh, yes, yeah.
That's a constant.
Is that in Fortran? Okay. Anyways, this example program runs, it computes the average speed. These numbers do not correspond to my travel distance or travel time, so we're not actually telling how fast the airplanes are going. But at least it's there's a prototype around, it's feeble, it's sensitive to lots of stuff, but if you're lucky, it will run your code and it will type check everything as it's supposed to do. And this is under continuous development, so next week it might be 10 times better than it is now. But I'm very glad that some of these examples actually work in this compiler so we can get them to run. And
so the subroutine test template.
Yeah.
The instantiate, is that runtime?
No, this is compile time.
Okay. So it's a declaration, like
it's a declaration statement. It's like a use statement. But it says instantiate.
Why do we have it twice? I'm wondering all the time. Instantiate travel template, instantiate travel template. I do not spot any single different character in these two lines.
No, and that's strange because they are actually doing the same renaming as well. So I think this is a copy-paste error.
Okay.
No.
It's one S from S and one was S from T.
Ah, yes. Okay, now I can see.
There was a difference.
There was a difference.
Difference.
And this explains some problem I had because I tried to use two imports. So import this, comma, import the second one, and that didn't work. So now I should have doubled my lines and done the second import down there. So maybe I can even make another example work in the break. These examples have been taken from me and rewritten into something which should be generic Fortran, then taken by the Fortran people and actually rewritten into something that works. So I'm not quite certain when I'm doing the right thing with the current prototype or when I'm doing something that we thought should work but doesn't work yet. But I could see if the operator notation works, but I'm quite certain it doesn't. No, it doesn't do it. And I don't think it will do the one without parentheses. Nope. So this was a discussion about the generic notation. And according to Fortran, it should be operated parentheses plus. That's more in line with the current notation in Fortran. And let's see if it works now after this. Yeah. Okay, so this is existence proof that we can actually edit generic program and get some type errors and we can fix it again and things work. Let's continue with the presentation here.
There's one more question again
Yep.
from the document. They say, I am confused here. If we have to instantiate ourselves, what is the point? Isn't the idea of templates that the compiler instantiates the right types for?
We'll get to that. And this all depends on the examples you have seen so far. So let's move on from this example and look at another example. I haven't gotten this to work in the Fortran compiler yet, but it's illustrative. So here I declare the type t and the function plus on t. And then I define the template, triple template, which is going to be based on the magma R declaration. For those who've been reading up some of group theory, they will know that magma is a binary operation on some type T. So it's a classical name. The triple body, I have three functions, one which does plus T twice in a left leaning expression, one which does the same plus T twice in a right leaning expression, and one which does the plus T call and then calls the plus operator on T down here. And in the equivalent templated version in C++, you can see that C++ is much more compact for this. I will declare type name T in the template argument, declare this as the signature or the declaration of a binary function. And then I will do the similar expressions. Here's a plus T, equal to plus T on the left. Here's a plus T and equal to plus T on the right. And here's a call to plus T. And I've replaced the setting call with the addition symbol, the plus operator. So I'm sort of matching up, and as I said, in Fortran we are block-oriented, and in C++ we sort of, in this case, we are doing just directly templates on functions. If you take away the declaration of the Magne, it's not much difference, even though Photon is very much more verbose in the declaration of functions.
Some of that is just the curly brackets.
Yes.
Whereas in Fortran you have end function.
Yes. So Fortran likes typing.
Yeah.
There's a redundancy in the language. And this is sort of pointing out, in the Fortran case, you would get the type error saying plus is not defined, single plus is not defined on the type T. Because Fortran doesn't know what type T is. It can be strings for that matter, or something else. Your own derived type without the plus operation on it. But you might have a binary function on your derived type. The template doesn't care because it doesn't know, but it knows that if you haven't explained the function up here, you cannot use it down here. In C++, by the way, they don't type check the template for this, so C++ will not flag any of these as problematic.
So what you're telling me here is that in order to make the left side, the Fortran side work, I also need to provide, like I had the function plus T, I need to explain to it what additions.
Yes.
Or require an addition or somehow.
Yes, I need to sort of relate that to the required declarations. And it has to then appear in the parameter list. Because type T can be anything, and Fortran cannot assume that it can do plus on type T. C++ on the other hand says, well, here's a template, and I'll figure out when we instantiate it, what is going to happen. So here are the instantiate statements. So in Fortran, I'm sort of explicitly saying that in this case, I want to use integers, operator plus. This thing didn't work, so maybe if I just copy-paste it and use two separate early statements, that it will work. Here I do the two computations. I cannot call triple E, because triple E was an error, so I had to remove that from my template. Over in the C++ world, I can call triple E, and it works nicely. Now, here I said that I didn't know which function this was, so I had to tell it that I'm using add integer. Here I'm instantiating it with real and operator minus. And here I'm using float, which corresponds roughly to real. And I'm using minus float, sort of minus wrapper on float. And in the last case, I'm instantiating triples with the maximum function. And over here, I'm then having my max float wrapper to send in. So these are sort of instantiations, and since this is parameterized by the plus t function, I need to tell what is my intention for this binary function. Is it addition, subtraction, maximum, or is it something else? So then we want to run these examples. So what should the value here be? Another break is coming up. So we'll finish this example and we'll take the break. So what should the value be if I'm computing this function with addition as my argument, integer addition, and the value is 7 or 2. This is 7, this is addition, this is addition. The result should be 21. 7 plus 7 plus 7, 21. The result here should be, again, 7 plus 7 plus 7, 21. And down here it's 7. 7 plus 7, it's again 21. So let's remember the first three outputs should be 21. The second case, I'm using minus. So what should the result be over here? So this is minus, this is subtraction and subtraction. So in this case, I have the value 7, minus 7 is 0, and minus 7 is minus 7. In this case, 7, because 7 minus 7 is 0, and this is 7 minus 0 is 7. And in this case,
have you overloaded the plus or is
this one is subtraction.
yeah, this one is subtraction, but here you have t plus t. So is the plus overloaded to be a minus, or is the plus still a plus?
The plus is still the plus, because
So
in
then
C++
it's,
it connects to the environment, and
So
in the
then this
environment
is 14, so then it's minus 7.
it's minus 7. But still minus 7 is plausible, because minus 7 is the result up here as well. Now we come to the last example. I'm throwing in the maximum function. So what should be our results then? The maximum of 7 and 7 and 7. Yeah, maximum of 7 and maximum of 7, 7, 7. And down here?
14.
Mm-hmm. So the thing is, we won't discover any error before we execute. We won't discover the error if we actually are doing addition. We won't discover it if we are doing subtraction, because minus 7 is a plausible answer. But we will maybe discover it because 14 may not be a plausible answer. But we have to be really careful to be able to discover this mistake, that we are connecting to the actual addition operation, the operator plus, and not using our intended semantics. Well, in the Photon case, this is flagged as on the previous slide as a type error already when you write the template body. So this is what you can get from having type checked
Where's
templates.
Could you just remind me, where's the Fortran case? So you said, then I tried to compile that thing, I get it.
Here. I don't have operator plus on type T,
Okay.
because I didn't include that in the declarations of the symbols I should be using and how I should be using. Oh, yeah. Well, maybe we should just pose the problems and then we take the break and you think about it and then we go through them afterwards. So I want to introduce a matrix library as a type-safe entity. So I need to sort of figure out what types I want to define, and I need to figure out what types I require to be able to build this matrix library. But then, of course, I also need to figure out what are the matrix functions I want to provide, and what are the requirements. Which operations, which functions do I need on my elements to be able to write the algorithm for my functions on the matrix. Is it time for a break now?
We can take a break, or we can wait like 10 minutes or something. I think we announced it was around 14.
Okay, so then we start to think, what are the answers to these questions?
I know you're right, so.
Not like pencil and pencil and paper.
Do we have pens and
Yes,
send it around?
You could in principle put in anything in a matrix. Like in paper and pencil, you can put anything in a matrix.
Yeah.
No.
Well, think aloud and can write down.
I think if you write on there, Magne, we can sort of get the camera too.
Okay.
Yes, I will turn it a bit. Then,
And
Let's
we
do
have
that.
a bit of more light.
I will also do that in a moment. Just
Oh, yes, this
say,
might-
how does it look now regarding the camera?
I need to get the other window. More. And no, sorry, too much. More back. This way. Bingo.
By now, do you want me to zoom?
Bit of zoom, yeah.
More
And
zoom?
perhaps- Yeah, and perhaps we have to stop sharing from.
I have to stop sharing.
No, yes, you could do that.
This is like a tiny pull step.
Yeah, if you stop sharing, then this will be much larger.
Yeah. No, people can choose that by themselves.
They can probably do that, yes.
Okay.
Okay, should I zoom more? Joachim, should I
I
zoom?
think this is fine. It looks like that.
Okay.
Okay, let's get the answers
Then I
now.
don't have focus. Is it out of focus or?
It should be focused on that white screen over there. But nothing has been written there yet, so I'm
Okay.
guessing that's what.
We need real.
Uh-huh. No, we don't need real, we need...
Element. Because you want a matrix of complex numbers, you want a matrix of integers, you want a matrix of reals, you want a matrix of my homegrown stuff.
So we need some type T for the elements, and we need some type M over here, matrix or something. Yeah. Operations. What operations should we have?
Condition.
Mm-hmm.
I want to add two.
Yeah. So I'll just write plus and assume that we know what it means.
I want to scale.
Scale, so that's
Multiply with the scale.
mult, and the scale would be T, and the return type should then be matrix. All matrix, and the return type should be matrix. So this is a mixture of C and Pascal notation, but it's shorter than Photon notation.
Now it depends on the type of matrix, whether you want a matrix product.
Yeah, I would say
If it's
that.
squarey, you might want it. If it's not squarey, it might be difficult because then you need to transpose and whatever.
But the matrix multiply we probably want, since it's a matrix. If it had been an array library, I would agree with you, but for matrix library, possibly want an mmult, even though we might want to sort of put additional requirements on what our matrix is.
Transpose.
Transpose.
But then, this is not funny.
And
So,
the
continue,
inverse matrix and the eigenvalue, there's a huge range.
Yeah, I would say maybe I want subtraction.
Yeah.
Maybe I want to have a zero matrix, an identity matrix. Oh, I'm running too fast now. Yes?
Now this for transpose can you put what you put with the scalar multiply? Because if I put in an n by m matrix, I get an m by n out. So I leave my space.
Yeah. So let's just say we're doing square matrices, so we don't need all that extra discussion.
That was what I asked you.
Yes.
You can invert it.
Mm-hmm. Invert
INV.
or division or solver, depending on where you come from, I guess.
Division.
How is that identity?
Yeah, it's
Identity, yes, the one.
the matrix is not division defined.
Yes, there is. You invert it and then multiply.
A lot of mathematicians would now get.
It's the same family of operations, basically. And if you define inversion, you can define division by multiplying, and you can say, well, division is solving a set of equations. The mathematicians don't do computations. They don't think about APIs. They think about what is easy to define.
You have the matrix multiplication upstairs, you have inversion here. So, okay, it's not so important. If I were to write it, you wouldn't know.
Well, I'm saying these are the same class of functions, so it doesn't really matter what I'm doing.
Yeah.
Okay, what do I need on this side to implement the plus algorithm?
Dimension. I need sort of. So we have a square matrix, so it carries one dimension. Is it a 1 by 1? Is it a 2 by 2? Is it a 3 by 3?
Yes.
Somewhere that needs to be on.
Okay, we need some size parameter, size n.
Yeah.
And now what do I need to do matrix addition?
I need the element addition.
Mm-hmm. So we need sort of T return T from the plus.
Somewhere we will need subtraction.
Okay, yes, if I'm doing minus, I would need subtraction.
I'm pretty sure it's inversion.
Uh-huh. And we probably need plus as well.
Which plus is that now?
This is the element plus. This is the element side.
We need element multiplication.
For what?
Multiplication.
Yeah.
We definitely also need a plus here.
Yep.
Because that is FMA instruction.
Wait a minute. If for this one I just need multiplication.
Yeah, it's one down.
The one down needs multiplication and plus. Yeah. Minus needs minus on the elements. 0 needs.
This is just initialization, and this is just fill everything with zeros.
Yes, but I don't know if my type has 0, so I need to have some 0 constant of type T. Yeah. And for identity.
I need the one
Yes.
neutral element of the multiplication.
But
And I need a 0 with the identity.
exactly. Because if this is going to be the diagonal matrix with ones, I need to have zeros on the corners. And that's the identity with matrix multiply. So now we sort of work through this example.
You have not done the inverse.
Oh, we need to do more down here. Yes. What more do we need?
It's a whole lot of things. Can we do the transpose first?
Yeah. What do we need for the transpose?
Essentially, I just swap elements, but then you always come up with stuff.
Or I can say, well, we don't need anything because we can move data values around anyway. If we assume that the assignment statement works, or swap or something like that.
What is this intermediate storage? So typically, if I do something like transpose, I have two storage cells, and I need to copy one out, copy over, and copy back in. So I need some auxiliary storage.
Yeah, so you need constructors and destructors for the elements you put in auxiliary storage.
That's hard if you fill up all the memory with the one matrix.
Yeah, it depends how.
So it's hard to do in place. Well,
It's impossible. At least you need one element to store one element.
Yeah.
And the same is for matrix multiplying. You cannot do that in place, you need extra storage. So this is also sort of a question, do you always assume that assignment is available? And I think in Fortran it almost always is. It's sort of just a few special cases where it's not.
But how is that this what works once works twice? So we had Jonas's stuff this morning. So type T, you didn't say that this is an intrinsic type. I could take some derived data type which I think up this morning, and this afternoon I want to make a matrix from it. And then if it's a derived data type, I have to, so for instance, Jonas didn't show any copy constructors, any. So if you, I assume this is not meant that this only works for real integers. If I cook something up on my own, and I want to make a matrix out of that, then in principle you then have to tell, okay, you have to, it's like this, I'm not looking into mathematical term, like real numbers, this has
Copy constructors and
yeah,
destructors.
so you need
and
additions, you need
assignments.
multiplications, neutral elements of here and there, so if you have to do
Yes, so you're sort of forcing the derived data type to have the operations necessary. But that's also one of the reasons I'm asking specifically which operations do I need for this algorithm? Because then you want to be able to use that algorithm even though you may not be able to use the other algorithms. But the stuff about constructors, assignment statements, I would like to leave that out of this discussion because that has more to do. Is there a protocol for how to use things in general? And I think that in these templates, we will assume that the data type has those basic things to go with it. This is always a question in C++ because they have not assumed the basic repertoire of things, and might have to explicitly declare these things as something we need. That allows you to get more fine-grained control over allocation of bits, which you probably don't want to get too worried about in bracket templates, because then you're not really getting to the meat of your problem solution. You're sort of losing an enormous amount of time with the administrative stuff to have things work. So maybe we'll force you for the time being to have assignments, to have equality, to have copy constructors, to have the necessary destructors to be able to run things without having to put all that stuff explicitly as template parameters.
So essentially what you're saying, certain of these things might just require by default.
Exactly. And I think for the moment we find that safer to say that this has to be there by default, rather than making the templates even more verbose to talk about those minute things which very seldom will be a problem in the practical use of these things.
Yeah, so I'm getting back where I was this morning with Jonas when he was splitting our pointers through. So if you have derived data types which have tons of storage allocated, let's say they have large array, and you copy it over, what do you copy over? Do you give a pointer that it points to the same thing, or do you so shallow versus?
Yes.
This is quite an issue.
Yes. But then with templates you might swap the question around. Should I have a matrix of your large data structure? Or should your large data structure contain matrices as their elements? So I have a large data structure of reals, typical situation, and I want to have a matrix of the large data structure. But if the large data structure was of type T, I could sort of say matrix of type T is the element of my large data structure.
I start thinking that I once had a very successful optimization project where essentially I can sort of explain that in a molecular dynamics code. So I have particles like Jonas said. And, so some of the things Jonas showed this morning from Instructor discussions we have. So I can introduce a particle which has a sort of a mass. If it's charged, then it has a charge, and then it has 3 position and 3 velocity coordinates. And then if I start building areas of those things, I get very poorly performing code, because most of the time I need to sort of average x position. I need just to add the x's. So on the cache line, I take one number, drop so many, then take the next number, drop so many, whereas in order to get performance, you should have an array of all the x coordinates of your particles in the system, an array of all the y coordinates that you can just have the streaming engine running through.
Yes, this was a good motivation for tomorrow.